Hello friends, Mr. Burrell here. We're just starting Unit 5. This unit is all about radicals and complex numbers. These are both terms maybe you haven't heard before in a math class, or maybe you haven't heard very much of in a math class. So if that's the case, that's all right, because we're going to talk about it right now in this unit. So at the very beginning, very first thing we're going to talk about in Unit 5 is simplifying radicals. I'm going to talk about what that means in just a minute, what I'm talking about when I say radicals and what it means to simplify them. But to prepare us for that, I'm going to review something you did quite a little while ago, but we're going to go ahead and find the prime factorization of the following numbers, of some of these numbers. So what do I mean when I ask you to find the prime factors, or the prime factorization of a number? So what I'm going to do, I'm going to look at this number right here. I'm going to look at 48, and I'm going to think of two numbers that multiply together to make 48. So for example, 6 times 8. 6 times 8 is 48. Okay, I'm going to break down each of those numbers even farther, like what two numbers would multiply to make 6. Well, 2 times 3 makes 6, and 2 times 4 makes 8. Well, 4, I could break that down further into 2 times 2. 4 is equal to 2 times 2. Can I break down 2, 3, 2, 2? Can I break down these numbers anymore? Not really, right? The only other numbers I could write would be like 2 times 1, 3 times 1, 2 times 1 times 1 times 1. So these numbers that I've broken 48 down into, so like 2 times 2 times 2 times 2 times 3, 2 times 2 times 2 times 2 times 3. Those are the prime factors of 48. Prime means a number that can only be divisible by itself and 1. So 2 and 3 are both prime numbers. So the prime factorization of 48 is 2 times 2 times 2 times 2 times 3. I've broken 48 into a multiplication problem with only prime numbers. So that's prime factorization. We're going to use that here in just a little bit when we're talking about simplifying radicals. So by the end of this video, these are the things that I hope you're able to do. I hope you're able to simplify square roots using prime factorization and simplify square roots containing numbers and variables. We'll discuss that here in just a little bit. So when I say radical, what do I mean when I say the word radical? You've probably heard the word radical in non-math senses, like, oh man, that's radical, far out, you know? That's not what we're talking about in the math sense. When I talk about a radical in the math world, I'm talking about this thing right here. Can you think of another word you would use to describe this symbol here? Have you heard it called anything else? Some of you may have heard this called a square root. A square root. And if you've heard it called that, you are correct. That is accurate. This is a square root. When there's not a number here, when this is just all by itself, I can call this a square root. In upcoming lessons, we're going to talk about how we treat these kinds of things when I have an index here, when I have a different number here. But without the number there, this is just called a square root. So something that you're probably at least relatively comfortable with. If not, we're going to discuss it. So what is a square root? What does it do? So for example, the square root of 49. What is the square root of 49? What does that even say? Well, if I were to go ahead and type that in my calculator, the square root of 49 is equal to 7. But why? Why is the square root of 49 equal to 7? Well, the definition of a square root is, say, if I'm taking the square root of 49, the square root of 49 is a number that when I multiply it by itself gives me 49 back. So the reason the square root of 49 is 7 is because 7 multiplied by itself twice, see that? 7 times 7 is equal to 49. So the definition of a square root of a number, like the square root of 49, is a number that when multiplied by itself 2 times would give me 49, or give me back the number underneath the square root. So, how do I simplify square roots? That's what this whole lesson is going to be about. So when we're calculating the square root of a number, we are just finding another number that when multiplied by itself twice, 2 times, is equal to the original number. So for example, the square root of 25 is 5, because 5 times 5 is 25. The square root of 36 is 6. because 6 times 6 is 36. See where I'm going with this? Square root of 81 is 9, because 9 times 9 is 81. Square root of 100 is 10. Square root of 121 is 11, etc., etc., etc. The square root of a number is another number that when multiplied by itself 2 times is equal to the original number. All of these ones, notice how nicely and how evenly all those numbers came out. The square roots of those numbers came out so nicely. There was no decimals, no nothing. I call those numbers perfect squares. Perfect squares. When I have a square root that comes out to a nice, perfect whole number, I call them a perfect square. Perfect square is what we usually call those. So what about this? What about the square root of 50? Well, if I were to go ahead and type that in my calculator, for example, the square root of 50, that comes out to like 7.0710, blah, blah, blah. It's a really gross number. I call that, if you remember back to our first unit, we call that an irrational number. An irrational number because it's a decimal that never ends. I couldn't write it as a fraction. So that's not as nice. That's not as nice. So what we're going to be talking about in this unit is writing these square roots, these radicals, in simplified radical form. So instead of writing it as a decimal, I'm going to write it in what we're going to call simplified radical form. So let me show you how that's going to happen. So for example, I'm going to show you how I would simplify this problem, and then I'm going to show you a unique kind of fun way that I like to remember how to solve these problems. So the square root of 50, first of all, I'm going to go ahead and break 50 down into its prime factors. So like 50 I could write as 10 times 5. 5 is a prime number, so I can't break that down anymore. 10 I could write as 5 times 2. And 5 and 2 are both prime numbers, so that is the prime factorization of the square root of 50. So I could really write the square root of 50 as the square root of 5 times 5 times 2. 5 times 5 times 2. Is that fair? Is that okay? Same thing, the square root of 50 is exactly the same as writing the square root of 5 times 5 times 2. Well, the definition, if I'm trying to take the square root of something, I'm trying to find a number that, when multiplied by itself, will give me that something that I started with. Well, look in here. Look underneath the square root. I have a number multiplied by itself. 5. Multiplied by itself. So if I just looked at the square root of 5 times 5, or the square root of 25, I know what that is. I call that a perfect square. The square root of 25 is 5. So if I just had the square root of 25, I would write that as 5. But it wasn't, I'm not trying to find the square root of 25. I'm trying to find the square root of 5 times 5 times 2. So this 2, notice, didn't go anywhere. It's still under the square root. So I would write the simplified version of this radical as 5 times the square root of 2. 5 times the square root of 2. So in your calculator, if you typed in the square root of 50, you'd get like 7.07. If I typed in my calculator 5 times the square root of 2, I would indeed also get 7.07. Okay? So that's how I go about simplifying radicals. That's all fine and dandy, but there's a kind of a fun way that I appreciate and remember, the way that I remembered to be able to simplify radicals is this thing called number prison. So if you haven't heard about number prison, get ready for a ride. You're in for a treat. So number prison, you've heard of different prisons. You've heard of the local prisons. You've heard of prisons like Alcatraz, some of these high security prisons. Number prison is the highest of all high security prisons. It takes doing a lot to get into this prison, and it's even harder to get out alive. It's very difficult to get out of number prison alive, and I'll tell you why. This right here is number prison. This radical is number prison. So let me show you something real quick. I'm going to break down 50 into its prime factors again, right here, 5 times 2, blah, blah, blah. So the prime factors of these numbers, those are the people or the numbers inside this prison. Really hard to get in here. Really hard to get out. The reason it's so hard to get out is because in order to escape from this prison, in order to escape from number prison, you have to escape in pairs. You have to escape in pairs. So if you're by yourself, you're kind of out of luck. There's no way you're going to be able to get out. You just can't. You have to escape in pairs. But the only dilemma when escaping from this prison is that even though a pair of you or two of you try to escape, only one is going to get out alive. The other one is going to get, I don't know, trampled on the way out, or they're going to get smushed by the security gate. Only one in those pairs is going to get out alive. So, the 5, this 1-5 gets out of prison. He's on the outside. This 5 dies. He is no more. He's out of luck. I apologize for that 5. And then on the inside of the prison, I have this lonely 2 left. So that's number prison. That's the analogy I like to use when simplifying radicals. So 5 became free, 1-5 died, and 2 was still a prisoner. So let's look at the example of 98. So 98, if I start by writing it in its prime factors, I could write 98 as like 49 times 2. 49 I could write as 7 times 7. So in prison, I have 7 times 7 times 2. Okay? But again, because this is such a high security prison, in order to escape, you have to escape in pairs. You have to escape in groups of 2. Okay, well, luckily enough for these 7s, there's a pair of them, there's 2 of them, so they can try to escape. But remember, one of them gets stuck in the chain link fence on the way out, and he dies. He doesn't escape. He's out of luck. It's too bad. But this 1-7 gets out. Good for him. This 7 goes away, and this lonely 2 is left still inside the prison. So the simplified radical form of the square root of 98 is 7 times the square root of 2. Okay, let's look at a couple other examples. We'll look at one of these. How about 180? So 180, let's write 180 as its prime factors. So 180 I could write as 90 times 2. 90 I could write as 45 times 2. 45 I could write as 15 times 3. 15 I could write as 5 times 3. I think that's as far as I can go. So inside my square root, I'll just write those numbers from biggest to smallest. 5, 3, 3, 2, 2. So 5 times 3 times 3 times 2 times 2. That's the prime factorization of 180. Well, remember in this number prison, in order to escape, you have to escape in pairs. So I have a pair of 3s, I have a pair of 2s, and then this 5 is going to be stuck. This 5 is going to be stuck on the inside. Poor guy. Too bad. So when these pair of 3s and this pair of 2s try to escape, remember the only one of them actually makes it out alive. The other one dies on the way out. It gets stuck in the electric fence or something. So I get a 3 and a 2 outside. And what are the 3 and the 2 going to do when they both get out of prison? Well, they're going to multiply. So I'm going to multiply those together. 3 times 2 is 6. So any numbers that get out of prison, they're going to multiply. So I'm left with 6 times the square root of 5. The 3 and the 2 got out. Their partners both died. And then the 5 is stuck left inside. Okay. So, if I just have a number underneath the square root, that's how I treat it. What about if I have variables? What about if I have these letters? What am I going to do then? Well, never fear, the process actually isn't that much different. So, here I have the square root of x squared and the square root of x to the 5th. So, remember the square root of x squared, that exponent is just another way of writing x times x, 2 times x multiplied by itself 2 times. Well, the same principle still applies. They're still inside the number prison. In order to escape, they still can only escape in pairs of 2. So, if these pairs of x's try to escape, remember that only one is going to make it out alive. One falls in a pit of mud and gets stuck and perishes while only one survives. So this x gets out, one x gets out, and there's nothing left inside the prison, so I'm not even going to draw the prison. The square root of x squared is x. What about the square root of x to the 5th? Well, x to the 5th, again, is just x times x times x times x times x 5 times. So I have 5 x's in there. Remember that all these x's, they can only escape in pairs. So these 2 x's and these 2 x's buddy up. This x is out of luck. He's just stuck in there. He's stuck in prison. And then when these pairs of x's escape, only one in each pair is going to survive. Well, if I have 2 different x's that get out of prison, what are they going to do? They're going to multiply. So I'm going to multiply those 2 x's together. Well, x times x is x squared. So the square root of x to the 5th I could write in simplified radical form as x squared times the square root of x. Okay. Let's look at a couple other examples. Now what if I have numbers and variables? What am I going to do in that case? Well, let's take a look. Let me go ahead and let's look at this middle one, and then we'll look at this big one on the end. So I'm going to treat them both the same way. Again, 48, I'm going to go ahead and find the prime factors of, because it's a number I'm going to find the prime factors of. So that's 24 times 2. 24 is 12 times 2. 12 is 6 times 2. And note that this isn't the only way I can break this down into its prime factors. Whatever 2 numbers you decided to multiply to make 48, as you break them down, you're going to get the same answers, the same prime factors either way. 6 is 3 times 2. So underneath this square root, let me write it up here maybe. Underneath this square root, I'm going to have 3 times 2 times 2 times 2 times 2. And then I'm going to have 7 z's. Z times z times z times z times z times z. 1, 2, 3, 4, 5, 6 times z. So I have 3 times 2 times 2 times 2 times 2 times z 7 times. So don't be intimidated because there's so much stuff in here. The same rules still apply. The same rules still apply, right? They can only escape in pairs. So this pair of 2's, this pair of 2's, this pair of z's, this pair of z's, this pair of z's, and then this z and this 3, well, they're stuck. They can't do anything. They're just stuck inside the prison. So 3 and z are stuck on the inside. They're going to multiply. And then all these other pairs, remember that only one in each pair is going to survive. The other partner is going to trip and land on their face or something. So 2 2's are going to make it out, and 3 z's are going to make it out. And with everyone that gets out of prison, what are they going to do? They're going to multiply. So 2 times 2 is 4. Z times z times z is z to the 3rd. So my final answer would be 4z to the 3rd times the square root of 3z. Let's do this one real quick. How would I break down 126? Well, 126, I think that's 63 times 2. 63 I can break down into 9 times 7. 9 I can break down into 3 times 3. So if I write this square root, wow, that was good. If I write this square root, I'm going to have 7 times 3 times 3 times 2, and then times x times x times x, times y times y times y times y, because I have 3 x's and 4 y's. Same principle applies. In order to escape from member prison, you have to escape in pairs. So I have a pair of 3's, I have a pair of x's, I have 2 pairs of y's, and then I have a 7, a 2, and an x that are all still stuck inside. Well, with who's stuck inside, they're going to multiply. 7 times 2 times x is 14x. And remember, the pairs that try to escape, only one in each pair survives. One of them inevitably is going to perish. And what do I do with all these guys that get out of prison? They're going to multiply. So I'm going to have 3 times x times y on the outside. 3 times x times y times the square root of 14x. Okay. So real quickly, kind of a real-world situation, word problem that you might see associated with these kinds of problems. This says, if the area of a square garden plot is 18 square feet, what is the length of one of the sides? So the area of this plot is equal to 18 square feet. Well, since this is a square, I know both sides are going to be the same. So x times x, because area of a square is one side times the other side, base times height, x times x, or x squared, is going to be equal to 18. Well, in order to solve for x, I would have to square root both sides, which would give me x equals the square root of 18. Well, the square root of 18, I could write that in simplified radical form. I could write that as a simplified square root. I would go ahead and break down 18 into 9 times 2 and 9 into 3 times 3. I would write all those prime factors underneath the radical sign. The 3's could escape in pairs, but only one of them would survive, and I'd be left with 3 times the square root of 2. That would be the length of one of the sides of these squares. So, that's it. Let me go back to these original objectives that I wanted you to understand. Hopefully now you're able to simplify square roots using prime factorization, both with numbers and with variables. I hope that was helpful. Please don't hesitate to reach out to me if you have any questions whatsoever, and I hope that you enjoyed that as much as I did.